To finish off the chapter, let us look at padding and padded oracle attacks. Padding messages and padded oracle attacks. Okay, this is mostly going to be done in CBC mode, okay, where it is the most convenient, because if you look back at CBC mode, which is used quite commonly, right? I'll just draw a picture to remind you how CBC mode worked. C0, and my message M1 was then XORed with my initialization vector, which hits with FK to give me C1. M2, okay, C2, dot, MT, okay, CT, right? It is important that the message have all the blocks of the same length. Important that MT, MI, I between 1 and T are all of the same length, right? Which might be unreasonable to expect from a standard message. And so how do we code arbitrary length messages? So the process is going to go message encoded data let me do this. Let me just, so the question we first want is what to do when arbitrary length messages. A-R-B-I, horrible spelling, A-R-B-I-T-I, arbitrary length messages. The answer is padding. Okay. The standard protocol is called PKCS5 encoding. Usually PKCS5 encoding. I say usually, but this is a common one, and that we will be looking at an example of this. There are, of course, multiple ways of doing this, but this is a standard one that we'll be looking at. So how does this go? The first thing we do is we have to change the message to match the length. So what the way it goes is message first gets changed to encoded data, and then it gets changed to ciphertext. How do we do this? For PKCS5, here's how you do it. So assume that the message is an integral number of bytes rather than bits. Assume the message is an integral number of bytes. Okay, since this is a real life thing rather than just random messages, it is generally encrypted with bytes. Okay, we'll denote by L the block length of the cipher. Denote by L the block length of the cipher. Okay, again in bytes. In bytes. Okay. So far we generally refer to this as N, but here we are going to use L. Okay. Let B greater than or equal to 1 be the number of bytes that need to be appended to the message. Be the number of bytes that need to be appended to the message to make the length a multiple of L. To make length multiple of L. Okay. Note, it is important that we take 1 less than B less than L. So B is not equal to 0. Even if your message is exactly length L, you should in that case append it by length L. Okay. And now what you do? You append B encoded in 1 byte B times. Okay. For example, if 3 bytes of padding are needed, if 3 bytes of padding are needed, then we should encode, then we should append 0x cross 03 03 03. Okay, you should make sure that it is encoded as 1 byte. 3 can be encoded using 2 things. Encoding of 3 is 0011. So to append 3, you actually append 03. That is 1 byte, right? 03 would be what is that? 00000011. Okay. Okay, that is my appended data, and that is what I'm going to then encrypt. Okay. How does decryption work? To decrypt, you're using CBC mode, right? So you use CBC mode to decrypt as well. Use CBC mode decryption to obtain encoded data. Okay, and how do you do this? So look at the final byte of the message. Say the final byte. of the message of the encoded data has value b. Okay. Then here's the process. If b is equal to 0 or b greater than L, return error. Okay. We will figure out why it is important to return error. If the final bits of if final b bytes of encoded data are not all equal, are not all equal, and especially all of them have to be equal to b, then you return error. Okay. If both of these conditions are indeed satisfied, then you just remove all these b's, which are b many of them, okay, and output what remains as the message. Otherwise, strip off the final b bytes. Of the encoded data. And output what remains as the message. Okay. So for example, if I was using L is equal to 8, example, L is equal to 8, okay, then I have some long message, blah, 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 and the final bits, final bytes look like this. AB 0, 1, 4F, 2, 1, 0, 0, 7C. Okay, so in that case, this is 6 bytes and my length is 8. So I need to append it by 2 bytes. And so the appended data 4, 5, 6, 7, 8 is going to look like AB 0, 1, 4F, 2, 1, 0, 0, 7C. Oops. Right? And now I have to append 2 bytes. So I'm going to write 0, 2, 0, 2. Okay? That's my padding. Okay? And so a padding oracle pads the message. Padding oracle. Oracle. Pad the message and then what do you call encrypted or decrypted, and they're used to pad messages. They're frequently used in web applications, for example. Frequently used presently. For example, in web applications. Okay, but the problem is, even if um, the attacker uh, only gets the message as error when you attack a padding oracle, a message encrypted with a padding oracle, they might still be able to uh, gain information. So even if an error is not explicitly returned, so if you change the last bit of a message, technically you would get an error, right? Even if you don't return an error, the attacker might be able to figure out something is wrong. An attacker might be able to detect differences in timing behavior, etc. So for all practical purposes, it's the same as saying, "Oh, you're getting an error." Okay, so how do we uh, present an attack against such a padding oracle? So we have CCA attacks that we have looked at before. We are we are going to improve upon that. And so main idea of attack is going to be as follows. Main idea of the attack. First, consider a two-block ciphertext. Uh, for example, I'm just showing this for an easy one. The book uses a three-block example. You can use that also. Just for easier purposes, just let us just look at a two-block ciphertext. Consider a two-block ciphertext. Two-block ciphertext. Initialization vector, comma C. Okay. So how do we get the encoded data? The decryption is encoded data, which is may or may not be equal to the message, is going to be fk inverse of C with the initialization vector, right? Since I'm using CBC format. Okay. Now here's what you should note. Observation. Observation. If I change one of the bits of the initialization vector, suppose the ith bit, then it's going to change exactly only the ith bit of the encoded data. If an attacker modifies the ith byte of IV, this causes predictable change only to the ith byte of the encoded data. Right? So for example, my message was fk inverse of c was something. I don't care. 9, 6, 7, 8, 9, whatever. XX, 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 XX. Okay, I don't care what the exact thing is. I have some initialization vector. Which I am XORing with, which don't care again what most of it is. 9E 02 7C 00 21. I assume that these are of the same length, by the way. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, sure, fine. Length 9. Wanted length 8, but whatever. 1, 2, 3. So I'm just going to color these out. I don't know. These are filled with something, maybe YYs. Then my encoded data is going to look like encode is equal to well 0, 6, 0, 6, 0, 6, 0, 6, 0, 6. There should be 6 of these, and some other garbage. Right? And now, if I change one of these bits, just give me a second. If I change one of these bits here to, let's say, if I change this one to make it 0, 1, it's going to affect only this bit, right? And suddenly I get an error. To me, that tells that there's a padding of more than 4 present in the message. Okay? If I did not get an error, I would know that, oh, if I change this bit here, right? Let's say I change this bit here. That affected this bit. I did not get an error. That means that part is part of the message rather than padding. Message. No error. Part of message rather than padding. Okay. So if I start working backwards from the last bit, second last bit, third last bit, so forth. Actually, the other way around. Start from the first one, second one, third one, fourth one. I can know at what point am I hitting an error, and that will tell me exactly how many bits are there, how much padding is there. Okay. So I have gained more information about the message. So what is the attack complexity? So you need less than or equal to L tries to learn the number of padding types, bytes, padding bytes, right? And generally this is going to be in bytes. And so you take 2 to the 8, which is 256 tries to learn each plain text byte. Okay. So what have we seen so far? We saw CCA security, a summary, okay. So we saw that CCA security attacks are actually a significant real world threat. Chosen ciphertext attacks. Real represent a significant real world threat. Secondly, modern encryption schemes are designed to be CCA secure. Okay, which means since we have never none of the scheme. Okay, let me say this first. None of the schemes we have seen so far. We have seen so far are CCA secure. CCA secure. Why was that true? Because they were all malleable. Right? We have not seen a non-malleable scheme. We will look at them later towards chapter 4. However, such schemes better exist because otherwise modern day security is crude, right? So modern encryption schemes are designed to be CCA secure. Okay? And that is where we are going to end chapter 3. Okay? And actually, let me do this. Let me stop this video here because what we are going to start now is going to be chapter 4, and I want to start it off in a new video. Okay? So let me just start off that in a new video. I'll stop this